So today we will address the kernel I/O interface. Yeah, the kernel I/O interface basically has two levels. One is the BlackLevel Protocol. One is the PO-level Protocol. And BlackLevel Protocol is the protocol that you initiate the module, and the PO-level Protocol that means how you transfer the data. Yeah, and in particular, in order to talk to the host programs, we basically use the following three AXI interface: AXI Lite, AXI Master, and AXI Strings. Yeah. So let's go back to look at that's the C code, and today we mainly cover this part. Okay, the function header part, and in particular, there is the function hierarchy that's defined mapped to the Verilog module level. And for the arguments, that's the module I/O ports and the data type. Okay, and so in here, the data type affect a lot of on the performance and the area a lot. Yeah, and there are protocols associated. Yeah. Okay, this give a very simple examples. So in this, when you take these modules and you go through the HL synthesis and doing the IP generation, eventually you will get the IP like this one. Okay, and this IP, first you notice there is a AP control protocol. There are some signal generated for controlling the block. This is BlackLevel protocols. And for others, the PO-level protocol that include the data ports and certain control signal or status signal. For example, like in here, there are three arguments, in one and in two. And these two actually has only the data port without any protocol signal associated with it. So that's the so-called AP noun protocol. I will explain it later. That means the data is a simple wires and doesn't need any handshake protocols. And for the output signal like the sum, this if you look at the sum, that's both the input and output. So it's an I/O port. So you will have input data ports and the output data ports, and also the related control signal associated with it. Okay, and for this module, it has a return value. So the tool automatically add a return port, return data port here. Yeah. So this gives you a very simple idea. Okay, first, for the module I/O interface, on the top function, in here I'm talking about the top functions. Okay, and it's different, the top function is different from the sub functions. Yeah, and for top functions, basically that's the kernel. The kernel has another role, which is communicate with the host. For other module, which is only the sub block of a top function that is only doing the data transfer between blocks. It doesn't communicate with host. So for the top functions, it has an additional control, BlackLevel protocol associated with it. And so for the I/O interface on the top functions, it has the following functions. First, you need to communicate with the host application program. Yeah. And you also communicate with the external I/O ports. Let's say that you have the FPGA chip. Okay. And then you have a kernel function. Okay. Then this kernel function may interface I/O. For example, there can be a camera input. And there is like a SPI or the camera, LVDS, or other I/O interface that's receiving the external peripheral signal and goes in. Yeah, or it could be have the AD converter if there's a sensor sensing the current or voltage. So when it's going to the ADC, it generates a stream of data. Yeah. So this external top function need to interface with the external I/O, or it communicate with the system memory. The FPGA chip has the DDR memory. Okay. However, the kernel function does not directly interface with the external memory. It goes through some adapter or some interface signal, particular like in pink. Okay, the DDR memory is on the PS side. So the kernel function actually interface with the XI ports and then go through PS side and to reach the DDR memory. However, yeah, that's one of the I/O function for the top function is access the memory. Yeah, and also the kernel could also interface with other kernel. Okay, you design, for example, if you have a chip, let me see, if you design the FPGA, you can design each kernel individually and validate each kernel. Okay, and then you have a multiple kernel, you can integrate them. Okay, so the interface could also communicate with other kernels. Yeah. So remember the role of the I/O interface for each of these type of interface. Most of the interface kernel between kernel will use a string. Yeah. So for those interface we introduced later, it has its own purpose of using that. Okay. So in today's lecture, you have to keep very conscious on this interface is on the IP level or in kernel level. So that's what we will talk here. Okay. When running the VTIS flow, you will specify whether it's an IP flow or the kernel flow. For the IP port, it will generate a simple IP. Okay, this IP mostly is interfaced with other IP, and maybe with a wrapper that talk to the host programs. Yeah. So that's the IP flow. So for the VTIS HLS, it's mostly it's the Vivado IP flow. So you use the block design. Remember, you use the block design to put the IP together and hook on the system components so that it can talk to the host program. Yeah. So for the you run the VTIS HLS, mostly you get the interface like the AP5 or AP memory or AP handshake. For those signals, that's a IP level. Yeah. So another flow is a kernel flow. Okay, kernel flow, it could talk to the host program. Yeah. So for this kind of flow, okay, so this is the kernel. Okay, and there are two aspects. One is the kernel as a block. How do you control the operation of this kernel? So normally it's from the host program to control it. So this so generate the kernel object to interact with the XRT. XRT is the driver running on the host side. Okay. So in here there are three type of protocol used. One is the sequential mode. That means the kernel is running in non-pipeline. That means you run the kernel one at a time. Okay. Another mode is running at the pipeline mode. So the kernel, before it's finished, then you can fix next pipeline data so that the kernel can run in pipeline mode. Or even the free running mode. Okay, so there are 3 operating modes for the block of this kernel function. Yeah. And for the data transfer, there are 3 types. One is if the argument is a scalar, then you can use a AAHLS interface. Or if the port is a memory or pointer type, that means you want to transfer a block of data, then you use the XI master. Okay, or use a streaming interface. Okay. So this table gives the default protocol for each type of arguments. Okay. Let's try to read this table carefully. Yeah. First, we have a BlackLevel protocol. As I said, we have 3 types of BlackLevel protocol. One is the AP control none. That means this block is running all the time. You don't need to start it. Okay, for example, in our lab 1 is a multiplication, right? In the multiplication, this module is a simple wire. Okay, A and B wire, and then do the multiplication and output. So that's a pure combinational logic. Once the port present the value, then you get the value immediately out. Okay, so this type you use the AP control now. Another type is a handshake and chain. Okay, we will introduce later. In here, that's a block level, and the other are the port level protocol. Yeah. Let's look at the argument type. If an argument is a scalar, okay, then the default is AP now. Okay, and if the block the return value, you will use AP control handshake. Yeah, and if it's an array, then they all use the AP memory interface protocol by default. And if the argument is a pointer or a reference, then if it's input, then it's a AP now. If it's I/O, they will use this protocol. Yeah. If it's a pure output, it will be AP valid. And we will explain the protocol later in detail. However, you need to know how to read these tables. And if the argument is specified as a string, then you will use the AP FIFO. Okay. Yeah. And for those interface, it's on the IP level. Okay, on the IP level. And this IP level, it can communicate with other IP. If this IP need to interface with the host program, then you need to use the standard XI master, those interface. Then you need to have an adapter. Maybe I can. Okay, maybe I will introduce how the AP the IP level interface to interface with the host program. There's a sequence of a process. Okay, for top function communicate with the host, let me recap some of statement I just have said. First, scalar input. Okay, so the previous protocol only on the IP level. So when it's coming into as kernel to communicate with the host, then for the argument scalar, it uses AXI-like interface. Okay, if it's a pointer to an array, that means you want to transfer big block of data, and you use the XI master. Okay, but you need a distance from the AXI light interface to set the base address for the DMA transfer. Okay. And if the argument is specified as a stream, then you will use the XI stream interface. And this, we have done that in lab 2, right? In lab 2. Yeah. And for the function return, the return port, actually the data is pulled into the XI light interface. Yeah. And BlackLevel Protocol, the communication, the BlackLevel Protocol to interface with the host, there is no physical signal from the host. Instead of use the XI light register. Remember in the lab 2, that we have the AP start, AP ready, and AP down, those signals. Actually, from the host side, we use the memory map I/O to program at this register. When you program the register, it generates the control signal to the top function interface. Okay, so XI light is very important. Okay, there are a few roles in the process. First, for the, oh yes, yeah. Okay, these two terms, there are two different concepts. Okay, memory map I/O, that means that's the I/O interface. However, we map to a memory address range. They call memory map I/O. In order to access this I/O device, we use certain address to access. Okay, so for those address, that if you recall that we're doing the block design, that we use the address editor to specify the address. Okay, so this address is the host program used to access this I/O device. Okay, so you use this memory address to rewrite the actually is a configuration register. Okay, and the configuration register, that register output becomes the interface signal to the IP. Maybe I should draw it. Okay. So you use the AXI light interface from host. Okay. And there's a adapter. I will explain that later. In the adapter, you will decode the address. Okay. First, this is very detailed internal design. You have a decode the address. Okay, and once they decode, then you will enable the configuration register to write into the register. Okay, and the register Q output, for example, it becomes AP start. Okay, and the IP start goes to your IP module. This is the AP start interface. And so for those, so this IP also have, remember, there is an AP down. Okay, that's the output signal. Remember, for the output, we cannot use the AP noun protocol. Because if it's AP noun, then we don't know when this AP down signal is valid. Right. So it always associates with a valid signal, here, this signal. It must associate with a valid signal, tells when this signal is valid. Example, yeah. So the protocol will be like a AP down from this IP, and also have a valid signal. So when this valid signal active, this down signal is, you can sample the AP down when the valid signal active. So for the design, you can see it will become a register, and the register has an enable signal and clock. The enable is driven by valid signal. The data input is the AP down. Okay, and this signal can be read out using the AAHLS protocol. Read that to the host program. Understand? Yeah. Oh, later I will slide to show the whole picture. It's actually in here. There's a whole oh, I didn't touch. Yeah. Yeah. So I will explain this, put everything together. Yeah. Okay. So for XI Lite, there are a few function or roles. Yeah. First, we use the XI Lite to transfer the scalar argument. Okay. So the scalar argument, just like that, you put into the register set. And that register will be present just like an AP start. Yeah. Simply present a wire to the IP, the kernel modules. Yeah. Oh, the function return value for this IP, it has a return port. Again, the return port will be written to the XILite configuration registers. And those registers, you use a memory map IO using a specific memory address to read the return value back to the host. Yeah. And also, XILite will be used to specify the base address of the DMA transfer. Okay, so XI master, when you access the memory, you need address. Where do you get this address? You will need the XI Lite to program the best address. Okay, and then when doing the master access, then it concatenate or combine the base address from the configuration register and with the counter or the sequential address, combine them, then becomes a system memory address. Yeah. Okay. So the XI Lite HLS will produce the C driver code. When you export the IP, also come with the driver code and the, remember you have a driver and you have the HWH file. That's a header file specify the configuration register, memory map IO address. And the actual driver code, then you code the driver code to access the hardware. Yeah. So this is the XI Lite. Yeah. So it's very important here. Yeah, I think most of the students not familiar with this concept, but for people in the industry, they are doing the embedded system programming. They quite familiar with this mechanism. Okay. And the BlackLevel interface protocol, as I said, the BlackLevel protocol is used for host application or driver control the kernel function. Okay, and there are three interfaces. So basically, this protocol specify when the design start to do the operation, and tells when the operation ends, and tell the design status whether it's idle or it's ready for new input. And those information is communicated by the XI Lite register. Okay. And for port level protocol, there are three interfaces. Then we will explain that in greater detail later. Okay, let's come to this. Okay, yeah. So when you run the VTIS HLS, then it will give you a report, the interface report. So basically, what you get is here. Okay. So when you run the VTIS HLS compiler, it generates an IP, and the IP with those interfaces. The interface include this part is the block level, and this part is the port level. Okay. Remember, those interface you cannot communicate with the host with those interface because with the host you need the XI interfaces. Those are the XI interfaces. You cannot directly communicate. So when you do the IP integrator, export the IP. When you export the IP, then it pull down the adapter. Translate those interfaces into XI interface. Yeah. And for the pink, let me. Okay, for pink, remember in lab 2, we introduced the MPSOC. So the PS part and PL part, they have those interfaces. Those are the XI interface. Okay. For the PCIe acceleration card, okay, then let's say that's the PCIe accelerator card. Okay. So the PCIe accelerator card, you have the PCIe IP. That's a PCIe bus. Okay. So all the data transfer, you have to do the PCIe IP. And this PCIe IP here is also XI interface. Either XI string, mostly is a XI string interface. Yeah. So when you design this kernel from the AAHLS, you also need an adapter, just like the in lab 2, yeah, in order to hook on the XI, so that you can all the traffic will go on to PCIe bus. Yeah. Great. Okay, let's go back here. Okay. Like for example, in this example, okay, there's a very simple address that we have this BlackLevel Protocol that is an AP control handshake, so it generates all those interfaces. And for the in1, the interface is AP handshake, so it generates the AP value and AP ACK. Okay, and for the in2 is AP FIFO, so it generates the FIFO interfaces. And for the in-out, it's a in-out port. It's a AP bus interface. That's the interface it generates. Okay. So when you export the IP, you will hook on the adapters, and the adapter will generate the XI interfaces. For example, for the block protocol, it will generate the XI Lite interface. Yeah, and this just a slave. It's an input port, so it's an XI slave. And this FIFO will map to XI string. Okay, and then for those memory pointer or array that will generate, will connect to the XI master. Yeah, and before, so that's why after the export the IP, then you only see the XI interfaces. Okay, but before it can connect to the like the PS side, the XI interface, you need some infrastructure stuff. Okay, remember in the block design, you have the IP, which is the XI interface. But you do not directly connect to the PSP interface. Remember, we put down the interconnect modules. Yeah, and if a stream, since the PSP interface doesn't have a stream interface, so you put in XI master to stream DMA modules. That's what I call the infrastructure components. Okay, and for those infrastructure components, it's really tied to the pink framework or XRT. They are all together. For example, for this version of XRT, I download this package. The XRT, the driver in the XRT is specifically for certain DMA IP for this infrastructure. So you cannot use different DMA IP. For example, the interface that like the U50, the package we download is use XDMA. Okay, so in the future, that I think XDMA is too low performance. I want something higher performance or support multi-threading. Then I may use QDMA. Okay, so if you want to use QDMA, do make sure you download the XRT with the QDMA support. So there will be different version of XRT. Yeah. So the DMA, the infrastructure IP you use has to be consistent with the XRT, the driver you download. Otherwise, it won't communicate. So the system will not work. Yeah. Okay, so then there's the infrastructure. So after the block design done, then you can generate the bit tree, right? Yeah, and the bit tree, then you can start running this FPGA. And in the host side, there's a host driver to communicate with all those, communicate with the infrastructure component and also communicate with the kernel functions. Yeah. Okay, right now you know the whole process. Okay. Okay, here, let's talk about the BlackLevel interface protocol. Okay, first, the BlackLevel protocol is specified on the port return. Okay, and this return port is for it's kind of a hook. It's a hook that the tool knows this BlackLevel protocol. It doesn't mean it has a return value. For example, for this kernel function, it doesn't have a return value. Okay, but you still specify port return. Okay, so you can think the return simply a hook that you to specify I want to use this BlackLevel protocol. This return does not tie to whether this function has a return value or not. Okay. So let's look at the AP control handshake. Well, as I said, that's a sequential execution kernel. That means the kernel can execute once. Okay, and then in order to start the kernel execution, you have to restart it again. Okay, so there are two key interface signals. One is the AP start, one is the AP down. AP start is from your host program to tell this kernel function to start execution. And when the kernel function finish, you will return the AP down signal. Okay, so the kernel can only be restarted after it completes the current execution, AP down. Okay, so if you retrigger the kernel before AP down return, then it doesn't function. It does not function. Yeah. So it can only serve in one execution request at a time. Yeah. So it's kind of a low performance. Yeah. Let's look at the protocol here. Yeah. So there are the following interface signals, and those signals all mark in the XI light configuration register. Okay, they are so. In order to assert, for example, in order to assert AP start, you have to program using the XI light to program certain register, so that that register generate this AP start signal. Same as AP down is the signal is output from the kernel function, and the AP down, the signal value will be latched in a AXI light register, and the host program can read that register in order to know the AP down status. Yeah, and this the interface protocol. So after reset, then this kernel actually is idle. Okay, until it see the AP start assert. At this point, you see the AP start assert. Okay, when it starts, then it can sample the input. Okay, in here, you can drive the input. Okay, so in here, this protocol is quite important because the host program and the kernel function actually are in two different devices. One is run at the host CPU, one is FPGA. And they are far away, and all the communication takes latency. And the latency is uncontrollable. You cannot control, say, oh, AP star and the data will take 5 cycles. Okay, first, those interfaces running in software definitely run long latency. I think the microsecond levels. Yeah. So if you know the hardware, in the hardware is run by cycle. And in software program, it's running by microsecond or hundred of nanoseconds. Okay, there's a different scale of timings. Yeah. So in here, remember when we draw the waveform here, that's the interface is on the cycle level. That's a nanosecond level. So this protocol said that when the AP star asserted, then the hardware will start reading the input. So in this case, you have to program the input first. Make the input valid first before you start. Otherwise, you could not, the hardware will sample the wrong value. You simply could not control. Next cycle, the data will appear. Okay? So in this protocol, yeah, when you assert the AP star, it starts sample the input. And when the input is sampled, it will assert the AP ready. Okay, so that means the input is a sample. And then the internal operation starts, and then when it's finish the computation, the kernel will assert the AP down. Okay, and associated with the return value if there is a return value. Okay, so the return value is only valid when the AP down is assert. Okay. Then there are few timing value is important. First is the latency. So why is the kernel function execution latency? How long it takes for the kernel function to compute? It's the latency is from the time assert the start to the AP down assert. So this latency. Okay. So when we talk about pipeline, we are talking about II. That's initiation interval. II means for pipeline how many cycles that the next data can comes in. Okay, that depends on the pipeline rate. Okay, so from this waveform, the II is defined from start to the AP ready. Okay. So one question that if we want to do II equal 1, so what the waveform will look like? We can try to draw it. Yeah. To my best knowledge, okay, we can look at the wait. Yeah. Okay, let me insert new slide. Okay, let's try to draw the II equal 1. How the waveform will be looking like. So let's draw this clock. Okay, and this start. Okay. So let's AP start. And that's all the input. The input has to vary actually before the AP start. Okay. And since I want to do the II equal 1, that means suppose this is the first data 0 input. When you can start the next data, so you must have a next data here, right? And then second data here. So when the ready should be assert. You have to assert right here, right? AP ready. Yeah, it's ready. That means you can have a second data, right? And yeah, and it's continue ready. So for this type, then that's kind of a and the AP down. It's really depend on your pipeline latency. Okay, so AP down you can maybe few cycle later, maybe start AP down. Then every cycle you generate one output, the return value. Okay, so doing that you can do the II equal 1. Yeah. So in this case, the AP ready could not assert when you sample start. Okay, let's say that I cannot if I assert the AP ready here. Okay, that means the next data this will be the next data coming here. So there will be II equal 2. Okay, so for doing the design for II equal 1, you have to assert the ready even before you see the AP start, right? Yeah, you cannot say, because it's synchronous design. Okay, synchronous design, you don't see the start here. Otherwise, then you will have a path that the start to ready. There will be a combinational path. This is a very bad design principle. Yeah, the timing will be too critical. Yeah, so normally the design, the kernel function doesn't see start until you sample it at this clock edge. Yeah, if you see the start here and then you assert the ready here, then the the best II you can do is 2. Okay. So you must have a ready assert before you see the start. So that implies what? That implies you must have a latch. Always sample the input. You have to latch the input before see the data. So that means you have a front-end buffer. Yeah, in order to do the II equal 1. But this is detail, yeah. So that's when you're doing the design, I want you to design II equal 1, then you know the only way is you put a front-end buffer. Always latch the input. Every cycle you sample the data. Yeah, so that you won't miss the input data. Yeah. Okay, so that's a AP control protocol. So let's see. So for the AP control handshake, it has to come for the top level. It come associated with the XI light. Because all the control signal has its corresponding configuration register, like AP star, AP down, AP idle. They are all configuration register. Yeah. So for this module, the kernel function, you can have multiple functions, then merge into one XI light. You use a bundle. Okay. And when you export to the IP category, that you also generate the C function for driver and the header file. Yeah. And you all know that to start the block operation, that you program the AP start, set the register AP start. And the block, once the AP start is asserted, the block start reading the inputs. Yeah. So one thing important is the data must be ready before start. So that means you have to program the data pool first, then you trigger the AP start. I repeatedly emphasize this point. Yeah. When the block complete the operation, that this kernel function will assert the AP down and AP idle and AP register. It will be set by the hardware output and then saved into the XI light register. Yeah. Okay. So in here, that's actually repeat the same thing. Okay. So for the host XRT, which is the host drivers, so you want to start the kernel function, you write 1 to the AP start. And the XRT driver wait for the AP down. Okay. Then when AP down is asserted, then you can restart the program. So that means using the AP control handshake, you cannot do the pipeline. You have to wait for the kernel function finish asserting the AP down. Then you can restart by asserting the AP start. Yeah. So that means this kernel function cannot pipeline. Yeah. You do one operation at a time. Yeah. Let's look at another one. Okay, AP control chain. Okay, that's for pipeline kernel. Yeah. So it actually add another signal called AP continue. Okay. The AP continue, that means the downstream module. Let's say that you have two kernel functions. Okay, you have the kernel function 1. And that output will go to the kernel function 2. Okay, and this AP down with the return value, the return port here. Okay, and for some reason, the downstream kernel function may not be able to take the input value because maybe its input buffer is full. That I could no longer talk. So it has the using the continuous signal. It acts as a back pressure. to do the flow control. So it needs a mechanism that I could, since my input buffer is full, that I could no longer to take a new input data value. Yeah. So use the AP continue signal. So when the AP continue is deassert, that means the kernel function, the function one, the upstream module has to hold the output value and stop generate new value. Otherwise, it will overflow the downstream module. Okay, that's we call the back pressure to doing the flow control. Okay, so it provides this mechanism. So as long as the continue is high, that means it can continue generate the accept the output value. Then the upstream module can continue execute. Yeah. So originally, I remember this protocol in last year. Actually, the AP control chain has been used for years, and mainly used for this pipeline kernel, cascade kernel, and doing the pipeline operation. It doesn't have a mechanism to communicate with the host. Okay, so until this year, 2020.2, this new version, I see the application that the host program can execute the kernel function in pipeline fashion. Yeah. Then later on, we will see how the AP continue used by the host program to do the pipeline kernel execution. It's I think that's a new feature in at least 2021 or 2020.2. Yeah. Okay, so original design, the AP control chain is for cascaded pipeline kernel function. They connected back to back using the AP continue to back pressure. That's the purpose. For example, like if you look at read this waveform. Okay. So when you will sample the AP continue, is when you assert the AP down. Okay, when you assert the AP down, that means I have already finished the operation. That and if you see the AP continue, then you can start next operation. Okay. For the next one, like the second operation, when the AP down is asserted, however, the continue is low. Okay, that means the downstream module could not take the input, so you have to hold the return value. You have to hold it, and also the upstream function has to stop, has to hold. Otherwise, the new input generate, then you will overflow the downstream. So yeah. So you hold the value until, and the AP down also have to hold it until you sample the AP continue high. Then you can start the pipeline operation. Yeah. Okay. So here, let's see how the AP continue can be used by the host program, host control, to do the pipeline kernel execution. Yeah. In here, you have to separate two independent threads of operation. One is this one, that's the input thread. Another is the output thread. Okay. And this two threads is running independent. Okay. You cannot have one thread hold the execution of another thread. If you write the embedded program, then you will know it will be non-blocking. The way you write the code will be non-blocking. Yeah. Later on, we can see how you can write the code. Okay, so there are two thread operation. One is input synchronization. Another is output synchronization. And input synchronization is the AP start and AP ready. Okay, and the output is the AP down and AP continue. Okay, the way you write the code is you have a one loop. You have a one loop, the code. Okay, and the first loop, the loop is input synchronization. So you check the start, you assert the start. Okay, you assert the start. Okay, and then you wait for AP ready. If it's ready, then you can write the AP start. So you have another loop is the input synchronization. You assert the start, and then you wait AP ready. If it's ready, then you assert the start. So you keep feeding the input until this kernel function no longer take further input. Because in this case, you can imagine the kernel function has a front side input data buffer. Okay, it keeps taking the input data. Okay, and then if the data is full, then you could not assert AP ready, okay, because I can no longer hold the input data. In that case, the output the host function then stop feeding the input data. Okay, that's the one thread, input synchronization. Another is the output synchronization. That composed of two signals. One is the AP down and AP continue. So in this output, the XRT will wait for the AP down. Okay, so you see the AP down assert, then you can write the AP continue to keep the kernel running. Yeah. Okay, and this two threads, so this is another loop. This another loop. This loop is wait for the AP down and then assert AP continue. So these two threads continue running, and you will not these two don't block each other. Yeah, so you can see the input keeps feeding until the input buffer is full. And the other thread is once you finish, then I tell you you can continue. Yeah. Okay. So the two process run asynchronously and actually is non-blocking in non-blocking manner. Yeah. Okay, let's look at this the waveform. Okay. Hmm? Hmm? Oh yeah. Okay. Hey, Yilin.
Oh,
Yeah.
I just have
yeah.
a question. So, did you mean that AP start is the control signal for the input data and AP
他们都听不
continue?
到是？哎，喂，依林 ，hold on。
Oh, okay.
If you have the sound, I have the sound here. Then confusing. But you cannot hear what he's talking. He's talking, right?
I can
Oh, I
hear
see.
Professor Long's voice.
So okay. So you have to turn on the speaker. Right.
My speaker is on.
Okay. Yeah. Speaking.
Okay. So my question is that, so did you mean that AP start is for is the control signal for the input data? So the AP start is high, and it means the input data is valid, and AP continue is the control signal to make sure that the slave is still running. So if the AP continue is high, then the slave will keep running, because I thought AP start is to tell the slave running. So if we have the AP starts, that it will tell the slave to run, and why do we still have AP continue? Thank you.
Actually, so for the kernel running, there are two conditions. One is the AP start. Okay, and AP star basically tell the kernel function that I have input data ready. Okay, and on the other side is from the back pressure from the downstream module. That's AP continue. Okay, so for the kernel function continue to run, first you need to have input data. Okay, and you also need to make sure that the downstream back pressure, the AP continue is active. Okay, so once you continue assert the AP star and continue asserting providing the input data, and the input data actually put into the input FIFO. Okay, so the input buffer has data that constitute the first condition that I have input data need to process. Okay, and for the kernel to continue SQ, that you will need to look at the AP continue, where the downstream continually allow me to SQ.
So is it possible that the kernel keep taking the input data, but it is not running, which means AP start is asserted, but AP continue is not asserted?
Yes, it's like, for example, to communicate with the host. Okay, host has to transfer the data back to the host memory before you override the output data, right?
Yes.
Otherwise, you continue generate the output, it may override the global memory, right? So you have to. So when can you assert the AP continue? When? Is I transfer the output data from global memory to host memory, then I can tell you AP continue, right?
Oh, yeah.
So how can you seamlessly, without any stall, to continue SQ? You can imagine I probably need double buffering for the output. For the input, so for the pipeline execution, that for the input I'm talking about, you need to have a multiple level of buffers to hold the input. Okay, so that the output, so the AP star can continue assert to feed the input data. Okay, and for the output, you cannot assert AP continue until you move the data result back to the system memory, right? It takes some time. So that means there is a gap that you will hold the the pipeline execution, because it takes time to move the output data back to system memory. Yeah. So how can you resolve this problem? You can use a double buffer at the output stage, and always assert AP continue if you can move the data fast enough before the new data generate. Okay, suppose you output, you have two buffers that you design the kernel in a way that the output buffer will be, let's say, okay, I create, this all depend on this is very important concept in order to run really high performance kernel function. Okay, so if I design that, I will allocate a trunk of output buffer memory in global memory, not just double buffer, because the double buffer that could be risky, because the kernel may be running faster than you move data back to the host. It's all depend on the latency. So suppose I have a ring buffer for the output. Okay, then I allow, and the kernel function just continue right to the output buffer. Okay, and the DMA engine is designed in a way that you always move the output ring buffer to the system memory. Okay, in that case, I can always assert AP continue. That means you won't store the kernel function. The kernel function keep generating the output without waiting for you move the data to the host memory, because you are sure you will not overflow the output buffer. Yilin, you understand this design
Okay, so
technique?
taking this way, so the AP continue is the likely acknowledgement signal from the host to the slave to tell the slave that the output data is well accepted.
Right. Yes. Yes.
Okay,
That's the
then
right concept. Yeah.
I get it.
But
Thank you.
that could be fake one, you know. So
What do
to
you
be
mean?
aggressive, you simply make sure you don't overflow the output buffer. And not necessarily you have to move back to the host memory, right? As long as you don't corrupt output data buffer.
Oh yeah,
Yeah.
because we can have a multi-level buffer to store the many
Right.
output data.
Yeah.
Yeah.
Right.
Okay.
If you have only single buffer, then yeah, you have to make sure you already transfer to host memory before the kernel can generate new input. Yeah. So to overcome that, if you have a multiple buffer, then make the design much easier.
So in this case, the AP continue is asserted when the output buffer is not full, right?
But can you hear?
Uh,
Or maybe yeah.
oh, I said, does it mean that AP continue is asserted when the output buffer is not full, right?
Right. Yeah. That's right.
Oh,
So
okay.
if you carefully calibrate the system timing, that you are sure you do provide very robust margin, then you just keep AP continue assertive all the time. Yeah.
If your output
And
buffer
yeah,
is
then
deep enough.
yeah. And that save this, then you save the synchronization between host and the kernel function. Yeah. Yeah, if after very detailed calibration and calculation, then you know once I have that much output buffer, then no matter under no condition, the kernel will overflow output buffer. In that case, then you can save the second output synchronization. You simply assert AP continue all the time. Yeah. And because the synchronization picks up the whole CPU time, right?
Yes.
Okay, so those design quite aggressive. Yeah.
Oh, I see.
Okay, but it can work. Yeah.
Yeah.
So
Then I guess
hopefully it's
this
clear
will
this pipeline kernel
yeah.
description.
So in this way, the designer said the throughput will be very high because the HP continues asserted always.
Right. So you can see this waveform. Let's look at this waveform. Okay, you have a data input and data output. Okay, so you want always feed the input data without gap, without pending on certain condition. And you want to output can continue generate the output. Yeah. In this case, you maximize the I/O bandwidth. Yeah. Remember, in the system, there are certain resource. For example, PCIe bus. Okay, how do you design a system? You say my design is optimum. Okay, when you say my design is optimum, how do you evaluate this statement? I will come in to look at whether the PCIe bus is fully utilized. Okay, if a PCIe bus is could not 100% utilized, then you come to maybe the computation resource is not enough to feed the data. Yeah. So for every bus, for every resource, you want to design in a way they are all fully utilized, like a DRAM. Okay. You say, I want DRAM bus fully utilized. Yeah. If you see the DRAM bus only have a utilization 50%, okay, then you should push the DRAM utilization to 100%. If it could not achieve 100%, then you come in to see maybe the data supply or data consumption is not fast enough. That means your computation is not done fast enough. Then you come in to push your computation. Yeah. Especially those resource utilization fall under the maximum utilization mostly is because of the synchronization overhead. Yeah, you really want to hide the synchronization overhead. Yeah, and this doing pipeline, yeah, that's the key techniques. Yeah. Okay, that's a host control pipeline. Yeah. Okay, this give you an example. The performance difference between pipeline and non-pipeline. And if you look at the textbook, there's a lab. You can try it out. Yeah. Basically, the kernel function is just doing the multiplication. Yeah. And one, you use the protocol AP control chain. That means the kernel will be executed pipeline. Another kernel function, the block protocol is AP control HS. That means it's run at the non-pipeline. Okay, then you run these two kernel and to look at the throughput, you find out that if you run with the pipeline version, okay, the runtime is much reduced. Yeah, so you get like 70% speed up. So you can actually run this example to test it out. Okay, next, let's look at the AP control none. Okay, that means continue running kernel. That means this kernel doesn't need any BlackLevel protocol. So it's a continue running. Once the input data change, then it computes. And there's no protocol involved. And this interface is very important for the stream interface. Okay. Okay, there are two mechanisms to do in the control. One is using the conventional like a state machine, a protocol control mechanism. Another one is use a data-driven control. Okay, that's important. Remember all the handshake. We have like a AP control HS. There's a handshake for the block level, and then you do the data transfer. And data transfer have another protocol. So you have a two-level protocol in order for the kernel function to do the job. Okay, and the block level protocol is an overhead. Yeah. And also the data transfer and the control are two different threads. And it involves the two threads has to do with the synchronization. Yeah. So it creates the overhead and make the kernel execution slow. Yeah. So the idea, the best, the most efficient way to execute the kernel is the kernel synchronization or the kernel control is data driven. That means data ready, I automatically start without depending on another AP control, another synchronization. You can imagine that's the most efficient, right? So that's so-called data flow architecture. Okay, data flow. So all the synchronization or control is driven by the data. Okay. So you will say that okay, to run the kernel, there are certain arguments. I need to set the argument before it can do the proper work, right? Yeah. But those arguments can be part of the data, right? Yeah. So you may design a string. You may design a string. Okay. And the string has the control string and data string. And these two strings actually bind together. So this goes to your kernel function. Okay, when the string comes in, you look at the control, and then you set the configuration. That's the argument, right? That's the kernel function argument. And then you start execute. So there is no sideband independent control sequence. Yeah. So it's very, very efficient. For example, I have a host, and that's a kernel. Okay. Remember how to make the kernel start running. First, I have using we have to set the argument, and then we have to trigger AP start, right? And then prepare the data within. Yeah. So would that be good that the host simply write the data, and without this sideband or another thread of synchronization, and the kernel start running. Yeah. So that's the using the string interface. Yeah. And so far, the host to do the string interface. Right now, we only see the string from kernel to host memory. Using string, using the DMA IP to transfer data, and then it becomes the string interface to the kernel function, right? That's we have to use that, but we have not seen the host simply write the data as a string to the kernel, because that's a very, very efficient. And why we do not see that? Because it needs another DMA IP, the QDMA. And the QDMA, I think they haven't pulled into their package yet. Yeah, until I think early this year, people realize there's a much more efficient mechanism. So people start trying out using QDMA so that the host can directly streaming into the kernel. Yeah. For example, does the kernel only need a very small amount of data? So every time I want the kernel to do something that I have to program, set up, spend a lot of time to set up, and then send the data SQ. So that to my trouble. Why not just directly write the data and in this time, this kernel has to be always waiting for the input. Yeah, waiting for what? Waiting for the FIFO, if the FIFO is empty or not. If the FIFO, that's the input string. Okay, the host continue writing the data to the input FIFO. So as long as this FIFO is not empty, then the kernel can execute, take the top of the data and execute. Okay, so in this case, this kernel function will use the AP control none. That means it doesn't need any handshake protocol. Yeah. So for host communicate with kernel through stream, and the kernel starts execution when data is available as input. In this case, we use the AP control none protocol. Yeah. Okay, so yeah, so that's the basic idea. Okay, so I think most of the example, you probably won't see, you will not see this host to kernel string, and because only this year people start putting into the package. Okay. Okay, I have the following two simple questions. After the question, we may break for 10 minutes. Yeah. Okay, first question. If you want to run, you may recall. Do you recall? Yeah, okay. Oh, I didn't change, okay. Oh, yeah, okay. Two simple questions, very simple, okay. If you want to run the kernel in a pipeline fashion, what is the BlackLevel protocol to use? Yeah, yeah. B, B? Anybody? Yeah. I think everybody can answer this. If a kernel is only communicating with the host through string, what is the BlackLevel protocol to use? Yeah. B2, yeah. Control now. Okay. So let's break, come back 11.